Hello everyone, welcome back to another video. So today we will discuss solutions for Leetcode weekly contest 426. I was able to solve all four problems in 38 minutes, but I made some stupid mistakes on second problem. So let's start with first problem. So here we are given an positive integer n and we have to return smallest integer x such that it is greater than or equal to n. And the binary representation of x only contains set bits. A set bit refers to a bit in binary representation of a number that has value 1. So for 5, binary representation would be 101, and the answer here is 7 because 7 is the first number which is greater than equal to 5, which has all bits set in its binary representation. Similarly for 10, answer is 15. For 3, answer is 3 itself because 3 itself has all bits set. So brute force solution would be to iterate from n to probably 2n. I think, yeah. Uh, so we can start iterating from n and go till 2n. And here is just 1000. So this iteration would be around at max 10 raised to power 3. And for each integer we can check the conditions for this set bit representation. How can we do that? Maybe we can one way of doing it is converting it into a binary string and then checking the first index from left, which is 1, and checking the last index, uh, which is also 1, and the whole string between should also be, or should only contain 1. This is one way of doing it. Another way of doing it is any continuous string of ones can be presented as 2 raised to power m minus 1, where m is total number of ones. So only one can be represented as 2 raised to power 1 minus 1, which comes out to be 1 itself. 2 ones is 2 raised to power 2 minus 1, which is 3. So 3 is binary representation of 1 is binary representation of 3. Similarly for p1s, its representation would be 2 raised to power 3 minus 1, which is equal to 7. So this way you can do it, or this way you can do it. So this is the brute force approach. Another approach is for any number n, find its finds find a number x such that x is greater than equal to n and x is a power of 2. And in this case our answer would be x minus 1. Find x greater than n. So we have to always find a number which is greater than n and which is also a power of 2. How can we do that? So to find x, we first find let's say d, which is log 2 of n. This will return a floor value. So for 15 it would return for 15 log 2 would be 3 point something, but this will return its floor, so 3. Now if you want to find its greater number which is of power 2, we increment d, and then our x would be 2 raised to power d minus 1. So this is the solution based on this observation. I wouldn't say these are observation, these are just property. So this is the solution for first problem, and this is just the simple implementation. I first found log 2, it's log with base 2, increment d, and I just return 2 rest body minus 1. So this is just I'm using a left shift operator. So d left shifts mean 2 rest. I'm just finding 2 rest body. This was first question, pretty simple. Now second question, this is interesting, not interesting, but some mistakes I did. As you can see, 3 penalties here. I will go to each penalty and show you what I was doing wrong. So in this question, we are given an integer array nums, and this array contains n elements where exactly n minus 2 are special numbers. One of the remaining 2 elements is sum of these special numbers, and the remaining element is an outlier. Now, what's an outlier? That basically outlier is defined as a number which is neither one of the original special numbers and nor the element representing some of those numbers. So n minus 2 special numbers, one number which is sum of those special numbers, and the last one is outlier. So we have to find that outlier such that we have to find the largest potential outlier. Um, so in first case, 2, 3, 5, 10. Now n minus 2 special numbers here could be 2 and 3. Then 5 would be the sum of those special numbers, and 10 would be outlier. So 2, 3 special numbers, this making sum equal to 5. So first 3 elements are used. Now our outlier is 10. In this case, also the special numbers could be minus 2, minus 1, minus 3, thus making sum minus 6 and the outlier 4. Similarly, here 5 ones could be special numbers and making sum equal to 5, and other 5 remaining 5 could be outlier. So there can be multiple outliers, potential outliers. We have to find the largest one. So A1, A2, and an minus 2. Let's say these are the special numbers. I'm just assuming they are not in any sorted order or in anything. They are just permutation, you can say, arrangement of original array. Now let's consider an minus 1 is my sum of special number, and an is my outlier. Now if you consider as an outlier, then the condition should satisfy, which is an minus 1 must be equal to a1 up to sum of a1 up to an minus 2, this whole sum. So from this condition we can say that if we consider an outlier at index n, element at index n as an outlier, the sum of other elements, so let's add an minus 1 on the both sides. So this would come out to be 2 into an minus 1. This would be sum of all elements from a1 to an minus 1. Or we can say sum of whole array minus the outlier. And this would be 2 into an minus 1. Now, to have this condition satisfying, we just need to check if there is an element which is equal to an minus 1. How can we check that? We know this, we can find this value by considering an index as outlier. So iterate over all the array and find this current as sum, which is sum of whole array minus the current element, which is considered to be outlier. Now current minus 2 divided by 2 should be equal to any of the element in the whole array. So the conditions based on this, our final solution should look like this. We will iterate from n minus 1 to 0. We will sort the array and iterate from n minus 1 to 0. Now the ith element is, we are considering it to be an outlier. Now if we consider I to be outlier, total sum of array minus the outlier should be 2 into sum x, and x is nothing but the sum of special numbers plus the number itself. So it would be 2 into x based on this condition. So we have considered this as the sum of special numbers, sum of special number plus all the special numbers. So basically 2 into x. So we find sum minus a of ai divided by 2 as x, and if we check if that x is present in the array except the outlier, there might be chance that it is itself equals to outlier, but in that case the number of the number of elements which are equal to outlier must be greater than or equal to 2. So we can't consider outlier itself as x. So this is the whole solution for this. We basically check all the elements from n minus 1 to 0 as consider it as an outlier and check other condition. Coming to this other condition is was the main point of the question, I would say. So let's start with the solution. First of all, I sorted the array. And why I am iterating from n minus 1 to 0? Because we have to find largest outlier. So whenever a condition will be satisfied, we will just return that value. First of all, I am storing the frequency of each element in the array. Then I am taking total sum of the array. Now I am iterating over from n minus 1 to 0. Now, if I consider ith element to be outlier, the sum of all other elements would be sum minus a of I. I will also decrement the occurrence of outlier. Now I will check if absolute of that sum mod 2 is 1. If this sum itself is odd and divided by 2 would not be matched with x because all the elements here are integers. If we divide it by 2, it would this condition would not be satisfied. So in that case, I'm just re-adding my outlier condition for further use. So when I'm going to next index, my sum should point to total sum of the array, not the current sum. Also, I'm incrementing the occurrence again, and I will just continue there. If the sum is even, then what would be our x? X would be sum by 2. Now I'm checking if that there is an element in our array by just checking its frequency. Now why I did this? Because uh, I shouldn't consider outlier as that element itself. So to handle that, I'm decrementing the outlier's frequency. After this, I'm re-adding the sum with a of I. So next index should consider the total sum of array. Similarly, I'm re-adding the frequency of outlier. And then this -1, this is not required because the input is generated such that at least one potential outlier exists in nums. So this is just to handle the compilation error when you return nothing. And let me show you what I did wrong. So the first case is, I think, here. What I was doing is, and I'm not sure why I got wrong answer in first one. No, not specifically, but in in second one I got wrong because I was checking sum could be negative, and I was checking sum mod 2 equal to 1. So negatives mod cannot be taken like this. So you can just handle it by adding an absolute there. That was one of the mistake. Another mistake was not doing this frequency, removing decreasing the frequency of outlier itself. If I don't do this, it might consider that outlier's frequency here. So this was another mistake. I think these were two mistakes which I was making and got these three wrong answers. Let's move to third question. 403 rank. That's too bad, I think. The wrong submissions costed me a lot. This is an interesting question. We are given and two undirected trees with n and m nodes with distinct labels from 0 to n and 0 to m minus 1. We are given two 2D integer arrays, ages 1 and ages 2. So basically given two trees and ages from u to v. Node u is a target to node v if total number of edges from path u to v is less than equal to k. And the node is always target to itself because in that the number of edges between two nodes would be 0 itself, and it is less than equal to k. So that is an additional, I wouldn't say additional condition, but just to be sure. And we have to return an answer array which shows where on each index there is maximum possible number of possible number of nodes target to node I of first tree if we have to connect one node from first tree to another tree, another node in second tree. And this connection is independent of each other. So what connection you made for node 0 would not remain the same for node 1. So basically remove the added edge before proceeding to next query. So let's try to draw this tree. 0, 1, 4, 5, 6. Okay. So what we have to do here is for each I from 0 to n, so the number of nodes in first tree, we have to connect it to one node in second, such that the total number of nodes, including tree 1 and including tree 2, has a path to the node I, such that the number of edges between them is less than equal to k. Now let me show you why answer is 9 for first case. For I equal to 0, for I equal to 0, so let's start with nodes in tree 1. What are the nodes in tree 1 such that the number of edges between that node and 0 is less than equal to k? It would be all the nodes. 1 to 0 there is edge 1, 2 to 0 there is edge 1, 3 to 0 there are edge 2s, 2 edges, and 4 to 0 there are 2 edges, and 0 to 0 there are 0 edges. So the contribution of first tree to answer is 5. Now if we connect this 0 to second tree 0, then what would be the contribution of second tree? It would be 4. How can that be? So 0 of second tree to 0 of first tree, 2 of second tree to 0 of first tree, so that has 2 edges. 3 to 0 again 2 edges, 1 to 0 again 2 edges. 7, 4, 5, 6 would have number of edges between the node 0 of first tree greater than equal to 3. 4 has 3, 5, 6 has 4, 7 has 3. Yeah. So contribution of second tree would be 4, and contribution of first tree would be 5. So the main point of this observation is the contribution of each tree remains independent. So for each node, we can find the contribution of first tree. So for 2 also, if you see the constraints, n is less than equal to 1000. So for each node, we can find the number of nodes in which has level less than equal to k if we start from that node as root. So if you start from node 2 as root, the number of nodes which are bit below level k, less than equal to level k from this 2 would be 5, because 1 is at level 2 from 2, 0 is at level 1 from 2, 3, 4 are at level 1 from 2. So we can find individual contribution for each node. We can find contribution for each individual of first tree in n square for loop, not n square, n into n log n. So we will iterate over all the elements from n. That would be n, and then BFS or DFS, so n log n. Now, how do we find contribution of second? Now, whenever you connect an edge from first tree to second tree, you are creating an additional edge here. So whatever contribution coming from second tree, if it is rooted at an element I, the all the elements which are at level k minus 1 from that node would contribute to this node. So for 0, if you are connecting 0 of secondary from that secondary's root, so from 0, all the nodes which are at level less than equal to k minus 1. Here k was 2, so k minus 1 would become 1, and so this subtree 0, 1, 3, 2, these four nodes will contribute to 0. Now why k minus 1? Because when you create an edge, the level decrease, there is an additional edge already. So we cannot consider up to level k because that would be added as k plus 1. So from secondary, we have to find a node such that its k minus 1 levels are are contains maximum number of nodes. We just need to find one node which has maximum number of nodes, and we will connect that node to our search node, and we will find the answer. So what would be the answer for that? So let's say for we have to find for answer I. First of all, we will check all the nodes up to level k in first tree. Then we will add the maximum node, which is giving maximum number of nodes up to k minus 1 levels in secondary. And this sum would be the answer for ith element. So this is the overall observation. For first tree, contribution up to level k. In secondary, contribution up to k levels k minus 1. And the constraints are low, so I didn't try to optimize it. I just wrote a naive approach. So first of all, what we are doing is we are creating adjacency list for both the graphs. ADJ1 is for first edges and ADJ2 is for second graph. Now what I'm doing is in second graph I'm finding maximum number of nodes up to level k minus 1. How can we do that? We first pick a root and then I run a BFS up to level k minus 1, add keep a counter to store number of nodes visited, and also keep a max number of node visited and take its max to the counter every time. Remember, I'm incrementing counter when I have checked that its level is not greater than k minus 1. So I have maximum number of nodes up to level k minus 1 in secondary. Now what I'll do, I will iterate over first subtree. So all the nodes on first subtree, so 0 to n. Then I will find the count of nodes up to level k. For when if we root the tree at I. So C and E here would be the contribution of that node in first subtree. Mx is maximum number of nodes which are coming from second tree. Then I'm pushing the total sum in my answer vector. I'm finally returning the answer. So this was the core idea of third problem. I wouldn't say it was difficult. It was observation based, more observation based, and 2000 is very less count, I would say, considering the recent contest. But yeah, it's fine. Moving to fourth question. Fourth question also has very less count of solves. I'm not sure why. So this question is similar to the third one. So just the second part of this question. But here we are given that the condition of target changes and there is no k input. K is not an input here. The condition here is that node u is target to node v if the number of edges between path u and v is even, and the node is always target to itself because the number of edges between the node and itself would be 0 and 0 is an even. So that is clarified here. Now this has a similar logic, I would say. 0 1 2 3 4. 1 4 5 6. Now let's try to understand the solution for I equal to 0, which is 8. Now for I equal to 0, what are the contributions from first tree? 0 itself, 1 and 2 are not, 3 and 4 are contributions because 0 to 4 have 2 edges which is even, 0 to 3 also has 2 edges which is even. So contribution of 3 from first tree. Now from second tree, if we connect an edge between 0 of second tree, which elements will contribute? This 0 would not contribute because it is the number of edges here, it would be 1, so 1 is not even. Other elements which will contribute is this one, this 3 will also contribute, this 2 will also contribute, and this 5 and 6 would also be contributing. Why is that? 5 to 4 to 1, so 2 edges, 3 edges, 4 edges, 4 edges, so even. Now the main observation here is, uh, let's finish the contribution part first. So there are 5 elements, so 5, total number of nodes 8. Answer here is 8. You can try adding a edge between any other node, but maximum answer would be 8. I just draw this to explain, to understand how the question will look, how the solution looks. Now we will try to use the same strategy as first question, as third question. So counting contributions on each subtree, each tree individually. So let's start with first tree, 0. So for this zero's contribution, we first find its level. So which is rooted at 2, rooted at 0, let's say. So 0, 1 will have level 1, 2 will have level 2, 3 will have level 2, and 4 would have level 4. Now the zeroth value, all the even levels would be contribution. All the even levels would have edge between each other, will have even number of edges between each other. Now try to understand this intuitively. So there are two parts of this intuition. One is that there is a direct edge from the rooted node. So there is a direct edge from 0, 2, and 4. Let's say this is on level X, this would be level Y. Now both are even because we have considered them that way. Now the number of edges between them would be equal to y minus x, and difference between two even numbers is always even. So even levels with even edges between two nodes which have even levels on a same lineage of the root of tree would be even in such a way. Now let's say they are not on the same node, they are on a different node, like this. So this is level 2, this is level 1, and this is level 2. Now if they are connected to an uh, they are connected, their connection point is a node which has level as odd. So in this case, the number of edges from one node to that common node would be even minus odd, plus another node would be even minus odd. So it would be odd plus odd. Even minus odd is odd, and again even minus odd is odd, and then sum of two odds will always be even. This is the case where the connection point is at level odd. Now let's say that connection point is at position even, level even. In that case, the first number of edges would be even minus even. Second number of edges would also be even minus even. Even minus even would always be even. Even minus even would also always be even, and this sum would always be even. So the number of edges between even levels, two nodes which have even levels, would always be even. We have considered all the cases. This is an intuition based proof. So try to understand in this, considering all these conditions. So this is the first observation. So if there are two nodes which have levels even, which can be rooted at any position, will have even number of edges between them. So if we have to find number of contribution for a node 4, what we will do, we will find all the nodes which are at level even from it. So for 4, there are what are the even number of nodes? Nodes which have even number of levels 0 and 3. So total sum would be the total number of nodes would be 3. For 0 itself, the contribution is 3. Now if we have to find for odd, we can extend this idea to have to find number of edges between two nodes which have odd levels. So try to extend this idea, you will find similar observation. So to find contribution from first tree, what we do is we find its level and find total number of elements of that level's parity. So for 2, it would be find total number of nodes which have parity equal to 1 of its levels. So for 2, contribution would be 2. So node 2 and node 1. So we were able to find the contribution of first subtree. Now how would we find the contribution of second subtree? That is also easy. So for 0, we have a parity as 0. Now, either we can connect a node from second subtree which has parity as 0, or second option is to connect which has parity as 1. Now we will always connect with an element which has maximum contribution of second subtree. So again, we will run the same solution in second tree and find level wise total number of nodes. And finally, we will take sum of these for each element from 0 to n. We will find number of nodes at that parity and max of number of nodes at 0 parity and number of nodes at 1 parity in second tree. This is the overall solution. So idea here is to process both trees independently and find the solution. But here the constraints are high, so try to optimize your solution. You need to optimize the solution. You basically have to run only two DFS or BFS, whatever you like. So first of all, creation of those adjacency lists. Then what I'm doing is I'm finding count of uh, nodes of level 0 or level 1. A count of nodes for each parity of levels. So first of all, I'm pushing a root 2. So it won't matter what you take as root. Eventually, even odd property will remain consistent whatever root you pick. That is checked by these two conditions. So I'm pushing the root, its level, and its parent. Then what I'll do, I'll pick those elements, increment the counter of LVL, so level, in this uh, vector of size 2, and I will iterate its adjacents except the parent. Now whenever I'm moving forward, I'm just making sure that I'm passing the parity of level, next parity of level. So currently LVL was 0, it will pass 1 minus LVL, which is 1. If it was 1, it will pass 1 minus 1, which is 0. So I'm keep switching the parity at each iteration, at each adjacent node. Now what I found here is I found number of nodes at parity 0 and number of nodes at parity 1 in second graph. Now similarly in first graph, what I will do is I will find the same property, total number of nodes for each level 0 and 1 of parity, and I'm also storing level of that node, parity of that parity of the level of that node. So again I'm pushing u root, its level, and parent, iterating over this. I'm incrementing sum of level plus plus, but additionally I'm storing the level of that element. Now I will iterate over 0 to n. I will first find total number of nodes that level of that level's parity. So for 0, what I will find total number of nodes which have same parity as of levels as 0 has. So 0 here has 0 parity, 3 and 4 also has 0 parity. So contribution of that 0 would be 3. If we had to find for 2, I will find its level was 1, then I will find its total number of nodes which has parity as 1 at of its level. So the contribution of first tree and the contribution of second tree would be just max of two levels, max of any parity, so 0 or 1, and that total answer I will just push into my answer vector and finally return the answer. So this was the solution for fourth problem. Let me just refresh and check my rank. Yeah, it's pretty bad just because of the incorrect submissions on second problem. Mm, if I wouldn't have made this, my rank would be, yeah, around 175 to 200. But yeah, that's fine. I will try to improve this. So for now, that's it from my side. I will try to upload video tutorials for consistently for now, from now on. And thank you for watching the video.